Force between current carrying conductors. Force between current carrying conductors. So what we're trying to do is this. Suppose you have two wires. Suppose I have two wires carrying currents in the same direction. So I got two wires, infinitely long wires, carrying currents in the same direction. What do you think about those wires? Will they attract or repel? So two wires are carrying currents in the same direction. Definitely there is an interaction between them. Why? Because they produce magnetic fields. So each one will influence each other. So when the currents are flowing in the same directions, which way will they experience the force? Will they attract or will they repel? Like currents in like directions we'll see. We'll see which one is what's happening. So this current I1 will produce a magnetic field in this neighborhood. Which way? At this point, it is into the board. So this thing over here, which I'm marking as B1, is a magnetic field created at the location of the second wire, but produced by the first wire. Get it? The second wire will produce a magnetic field here. Which way? Outwards. So the magnetic field produced by the second wire here is going to be outwards. The magnetic field produced by this current is inwards here. Now, so look at this wire alone. There is a current flowing. There is a magnetic field subjected to it. So definitely it will experience a force. Which hand?
This
one. Left hand. Fleming's left hand comes there. So apply the Fleming's left hand. Magnetic field is in. Current is up. And so the force is to the left. So the force F2, that is the force experienced by F2, is depending on P1 and what else? The force depends on what? What's the formula for force? B, I, L. Yeah, but when I say infinitely long wires, then where is the L coming from? And therefore, instead of calling it force, we are more interested in finding force per meter. We don't want the real force on the entire wire. We want the force per meter. You get it? So the force F2 per meter is simply BI. So F is equal to BIL. So F over L is the force per meter, which is simply BI. You get it? The product of B and I will give you force per meter. Simple. So what is F2 per meter? It is B1 I2. But what is B1? What's the formula for the magnetic field next to a mu naught I1 over 2 pi A, where A is the perpendicular distance between. So that's the formula for B1. So put that B1 there. Mu naught I1 over 2 pi A times that I2. So that is the force per meter on the second wire. Think about the same things, what's happening on the first wire. On the first wire, magnetic field is coming out. Current is going up. Which way is the force? To the right. That's a force F1. So current is going up, magnetic field is going, magnetic field is coming towards you. Current is going up and magnetic field is coming towards you. So the force is to the side. So what is this magnetic field B2? B2 is mu naught I2 over 2 pi A. So if I find out what is F1 per meter, it's going to be B2 I1, which is mu naught I2 over 2 pi A times I1. What do you see from there? They're the same. So F2 and F1 are basically the same. What law? Newton's third law. These are Newton's third law pairs. These are magnetic forces. Remember I told you the type of force should be the same. If one is magnetic force, the other should be magnetic force. There it is. And they are equal and opposite and all those things. So yeah, these are third law pairs. They have to be equal. It doesn't matter what current is flowing here. Maybe 40 amperes here and 40 milliamperes here. Doesn't matter. The forces are going to be the same. So the force between wires per meter is mu naught I1 I2 over 2 pi A. Now if they are the same currents, then it will be just mu naught I square over 2 pi A. Got it? What if the currents were in opposite directions? What if the currents were in opposite directions? Now find out which way the forces are and all that. So this current is producing a magnetic field here, which way? Inwards. This one is going to produce a magnetic field here, which way? In or out? In again. Because you can see this in, this in. Okay? Now apply Fleming's left-hand rule. Not right. Some of you are picking up the wrong hand. Dangerous. Pick up the left-hand rule. Find out here. Magnetic field going in. Current coming downward. Current is this one, FBI. Okay? Current going down. Magnetic field going in. So the force is to the right. And look at this one. Current going up. Magnetic field going in. Forces to the left. So they repel. So when you have a cluster of wires carrying current in the same direction, they kind of stick together. So that's good. Whereas when you have currents going in opposite directions, they kind of try to separate because of the magnetic fields. That's also good. Because you don't want them to come get closer. And the magnetic forces and all that depend on like how strong the current is. Because the stronger these are, the forces are going to be strong as well. All right, no questions on this? So if you are given questions like suppose you have a wire going that way and it carries a current of 20 amperes, and I have a loop of wire. I have a single loop of wire which has a current of 4 amperes going like that and coming back. What will be the force experienced by this loop? What will be the force experienced by the loop? So how do you do this? Of course you're given distances. You're given all the distance. You're given the width of this loop, the length of this loop, the distance from here to here, all that is given to you. So if the distances are all given to you, how do you just proceed with this? The same way as we discovered those. This wire has a magnetic field. What's the magnetic field that's present over here due to this? So use right hand. So it's going to be inward. Now, Left-hand rule. Magnetic field is in, current is going this way. So which way is it experiencing force? Upward. And that force is given by what formula? Now you know the length. You can use that length as well. So you don't have to find force per meter. You can actually find the real force, BIL. So this force is going to be BIL. L is given, I is given, and B at this location can be found out, right? So you can find the force. What's happening here? The same kind of magnetic field is applied here, but less in intensity. But the current is going the other way. So which way is the force? Current is going this way, current is going that way, and the magnetic field is in. Okay? You're using the other rule?
Yeah, I'm used to the
Is it left hand or right hand?
yeah.
That rule uses right hand or left hand?
What?
The rule that you're trying to do something.
I find out the force and the direction of the force.
Yeah.
Not that.
Use left hand or right hand? Not right?
No, I'm trying to find the direction of the force, not the.
Oh, using Fleming's left hand rule?
Yeah, but it's just another different way.
Yeah, that's why I'm saying I can see that you're kind of having a different sort of approach. Telling you again, dangerous. Yeah, don't. I mean, if you're not, I'm not against it, but yeah, you can use it. But there is confusion waiting for you, especially when you go to the next chapter. You won't be as fluent. You'll see how much you'll have difficult. I mean, like I'm just saying this because I've seen the difference between how students kind of easily go through the situations with Fleming's left-hand rule, right-hand rule, and the grip rule. But the other rules can actually kind of confuse you here and there. All right. It's okay to use any method. The book is giving a different method. It's fine. But as long as you use the same method and properly do it without any confusions, then it's fine. All right. Come back here. So this force is going to be downward. But obviously it's going to be weaker, right? Because it's far away, the magnetic field is not as strong. So this force is definitely a stronger force compared to this. And what about here? Is this current going to experience a force? So the current here is going downward. Is there a magnetic field here? Yes. So will it experience a force? Magnetic field is in, current is down. So it's experiencing a force this way. What about this? This way. So they kind of cancel off. These two are going to cancel off anyway. And the other thing that you should notice is this. Over here, the strength of the magnetic field is stronger. So the force over here is bigger. And the force gets smaller as you go away. The same situation here. You know what I mean? But it will be even on both sides. So it is definitely going to stretch the wires a little bit. But other than that, it's not going to do anything else. But the net force is mainly because of this and this. So the net force is that way still. Okay, so understand how to kind of go into some situations like this and then see how you can apply the electromagnetic principles that you've learned. Moving coil. Moving coil. So when you have a coil placed in a magnetic field, now what's a coil? You can have a coil that is coiling like this, or you can have a rectangular coil. A rectangular coil is something like, that's a rectangular coil. The wire will go on the outside. No, just a loop. Just a loop like that. You can have multiple loops, but one loop is enough to kind of discuss these situations. and that loop is placed in a magnetic field. So don't draw the entire diagram till I tell you to do it. Okay? Now, that's a magnet. That's a magnet. Here's another one. Okay. So we have a magnetic field. In this case, the magnetic field is going that direction. Magnetic field is going that direction. And I'm going to place this coil here. I'm going to place the coil here. So if I place the coil there, I can draw it three-dimensionally so you can actually see the situation better. Yeah. If I'm going to place the coil vertical, this is how it's going to be. So this is the axis. You see that coil? It's like this. The coil is like this. Not getting it?
What is this?
Huh?
So it's like this in the.
No, it's straight down. It's placed into it. So yeah, this is how we can isometrically kind of show the view. Okay. If I simply draw it like this, you will not understand what's happening. Now that's a north, that's a south. If I put a coil like that, that's a coil.
Where's that?
Axis is that way. It's actually like this. Yeah. The coil is like this, and the axis is this. Now this is an isometric view, so you're actually seeing it like that. Make sense? So if I send a current from here, if I send a current from there, the current is going like this, like that, like this, like that, like that, come back. So let's find out what's happening. What will happen to that coil? So there is a current flowing in this manner. Which way is the magnetic field? The magnetic field is B, in that direction. It's a uniform magnetic field, as you can see here. It's a uniform magnetic field. So what will happen to this wire? Let's discuss that. Use Fleming's. Which way is the current flowing? Towards you. Yeah, understand that this is towards you. So the current is flowing towards you. Magnetic field is going that way. So which way is the force? Up. So this will experience the force upward. Now what about here? Current is going in, and the magnetic field is that way. So the force is down. What about here? Magnetic field is that way, current is upward. Which hand are you using? Okay. All right. So current is upward, and magnetic field is that way. So which way is it? Into the board. Yeah, this is into the board. That's into the board. And over here, it's going to be out of the board, like that. Just make sure you understand what I'm trying to draw here. Well, on a two-dimensional picture, I cannot draw that. That's why I have to do it this way. So forces are actually pulling it this way. So what's going to happen to the coil is it's having a tendency to stretch. Other than that, nothing is going to happen. The coil simply has a tendency to stretch, and nothing more is going to happen to that coil. Now let's look at a coil which is placed in a different orientation. Now you can draw. Now you can draw because now I'm going for the real picture. Okay. So the magnetic field is this way. So the magnetic field is that way, and this time I'm placing the coil horizontal. Previously I placed the coil like this, Now I'm placing it like this. Make sense? So if I'm placing it like that, that's going to be the coil. And as before, that's going to be the axis. That's the axis. You can have more than one turn of the coil, but just to understand the situation, you can always get it. So, all right, so we have the coil there. As before, I'm sending a current in. So the current is going to go like that, and like that, like that, and like that, and back. Now let's find out forces. Left hand rule. Go to each wire. Let's go to this one. This is a current going which way? Towards you. Magnetic field that way. So fix it. Up. Exactly. So magnetic field is going that way and the current is going towards you. So the force is upward. And what's that force equal to? B, I, and L. That's L, length of the rectangular coil. The length, this thing. The length of the rectangular coil. What's happening here? Current is into the board. Magnetic field is that way. Force is downward. It's the same force. What about here?
No force.
No force. Why?
The field and the current.
The field and current are parallel to each other. No force. Same way, no force. So these two are not really taking part at all. So there are only these forces. What is this force going to do to the coil? It's going to rotate it. It's going to turn it. Not a permanently turning thing, but it's definitely attempting to turn it. It is this idea that we use in motors later on. The same idea. But let's see, what happens right now is there is a tendency to twist it. So there is a torque. There is a torque. So what is a torque? What is torque defined as last year?
IL.
FD, force times perpendicular force times perpendicular distance. That is a torque. So about this axis, so the width of this coil is W. The width of the coil is W. So this force about that perpendicular distance from the axis, and this force about the same perpendicular distance from the axis. So it's like W over 2 and W over 2. So F times W over 2 clockwise plus F times W over 2 clockwise. Both are clockwise. Correct? So basically it is F times W. F times W over 2 plus F times W over 2. The total torque by this so-called couple. This is what you call as a couple. So there are two of them who are always opposite to each other. That's why they call couple. Look at that in real life too. Why they call couple? Because they are equal, or at least they think they're equal, and they're always opposing each other. All right, go back. So what is what is force? B-I-L. Oh. B-I-L. And perpendicular distance, W. That's a torque. So it's going to get a torque acting on it, B-I-L-W. But what is L-W? area of the loop, area of that rectangular coil. So torque is BIA. And this is if there's only one loop. What if there are n turns like that? You know, like loops are not always one. We have maybe 50 times or 100 times. Because if you want more torque, you want more number of lengths. So if you have n turns, for n turns, the torque is going to be equal to BIAN. The torque that is going to act on this loop is BIAN. When this loop is in this position. So when the loop is in this position, it experiences a torque of BIAN. And because of that, it's going to turn, right? But once it turns and goes here, what's the torque here? We already discussed that. Nothing. We saw that the forces were all going opposite to each other. So when it comes to this point, there's no torque. But then because of the twisting action, it gains that momentum. So it goes to this side. But when it goes to this side, the forces are going to be pulling it back again. So if there was a coil like this, and if I just sent a current, it's supposed to just oscillate like that and finally come to rest here. Right? It should finally come to rest here. It's not going to stay like this. Why? Because the force that actually was acting on this was upward and this is downward. And now it is going to be counterclockwise torque. This was a clockwise torque, but when it goes to the other side, it's going to be counterclockwise torque. And so it has to return. So I can't use this as a motor. Why? Because the motor needs a torque in the same direction always. You want it spinning all the time. Whereas this is not going to spin all the time. It's just going to flip and come back again. So it's going to twist. B, magnetic field. It's a uniform magnetic field, it's fixed. The current that you're sending is I. Area is fixed. Number of turns fixed. So these are all fixed. So what you can see is the torque is proportional directly to the current. So if I send more current, I'm expecting bigger torque. More current, more torque. But then any current will make it perfectly vertical. So if you want to do some kind of a comparison, what we need now is a spring. I'm not going to let this coil stay like that freely. Instead, I'm going to put a spring like this. It's a spiral spring. Now it is actually a spiral spring right there. So if this is trying to twist that way, it is winding the spring. Get it? So it does not freely go. Now the spring is released. When it goes like this, the spring is getting wound. So therefore, this torque is going to fight the spring, basically. So it will not settle like this. Instead, it will settle at an angle. You send more current, it can fight a little more, right? It can twist the spring more and more depending on the current. So more current, more torque, and it can twist the spring more and more. That is the idea that is used in a moving coil, ammeters and voltmeters and all those things. Didn't we discuss that earlier? So what is exactly there is this. But this one suffers a problem. That is, so basically the torque is proportional to the current. But in this case, there is an issue there. The problem is this. Watch. The problem is, when is the torque maximum? When it is horizontal. Well, because the force upward and downward here. So maximum torque is force times the perpendicular distance, which is the width. But once it twists like that, what's the perpendicular distance between this force and that force? Is it the same as the width? No more. So when the coil goes to this, from this position, from the horizontal, when it was horizontal, the forces are like that. When the coil turns like this, the forces are like that. So definitely the torque is not going to be big enough. Why? Because over here it was the width, and over here it's going to be only this component of the grid, that one. And once a coil comes absolutely straight, then there's no more torque. There's no perpendicular distance, like the same line. Make sense? So what you understand from here is, when you send some current, it will twist to some degree. Now you may have to send much more current to twist it by a similar angle, because you're not getting too much torque here. And you will have to send bigger and bigger currents to get it like this. Impossible to get it like that, unless the current is really high. So the twist will depend on the, so initially you can get it twisted from here to here by sending maybe 1 ampere. But the next 1 ampere, so if I increase the current to 2 amperes, the next 1 ampere is not going to twist at the same angle. It's going to twist only little. Why? Because of the perpendicular distance is getting shorter. So as the perpendicular distance gets shorter, everything is going to come down. So that you won't get much torque as it goes like that. Make sense? And therefore, you will have a scale that is not linear. So, see the attachment, I'm going to make one more attachment here onto this device, which is the pointer. That's a pointer of the instrument. And then here is your scale. You can see how the whole instrument is constructed. So on this scale, the calibration will not be evenly spaced. For this reason, that the torque is not even. You get it? So this may be 0 amperes, and that may be 1 ampere, and that may be 5 amperes, that may be 50 amperes, it depends. So it won't be giving you a linear scale, and the main issue for why it is not linear is because the forces are acting always up and down, and so the perpendicular distance is not able to, the perpendicular distance is getting shorter and shorter, which means the scale and everything is going to be affected. So what is done to rectify this problem? Have you successfully drawn it? You want to take a picture before you go ahead? I mean, if you don't want to, it's fine.
The point won't go past straight up.
Yeah, it cannot go more than that, because if it goes to the other side, it's going to return it back. Yeah, so it can only go that angle. Now, what is the modification that is done to rectify this issue? The modification is on the magnetic field. Because the problem lies on the magnetic, the problem is actually on the fact that the magnetic field is alright. So the magnetic field should not be uniform. Like we had a uniform magnetic field. So now what we need is a radial magnetic field. So the magnetic field is changed to this shape. So the magnet is in this shape. The magnet is now shaped like this, north, south. Now what is the advantage of having a shape like this is because the magnetic lines, look at the magnetic lines. The magnetic lines are like that. And from here, it's not going to be straight. It's going to go like this. And from here, it's going to go like this. The magnetic field is going to shape according to the shape of this. So, the shape of the magnetic field is now like that. What's the advantage? The advantage is when the coil is horizontal, like that, the magnetic field was this way, So it experiences the force as I have indicated. Can you see that? Now what happens when this coil spins to this angle? The magnetic field is still perpendicular. Can you see that? The magnetic field is acting from that angle. So even when the coil is gone, even when the coil is turned like this, the forces are always going to be this way, perpendicular to the coil. Yeah.
Well, the same effect we had if we use a radial coil or a uniform magnetic field.
Radial what?
A radial coil. So a coil that goes in a circle rather than a square.
Oh, coil doesn't matter at all because after all it's only dependent on the area. So you mean a circular coil?
Yes.
A circular coil doesn't make a difference because the torque that is making it turn, that's all matters, and that depends on the area. So if you make a circular coil, you're distributing the area altogether. So you can have circular or rectangular, anything has, because the area is the only. So you saw that torque is equal to BIAN. So A is important, not the shape. So area is length times width here. But if you're having a circular coil, it will also work. But that will have its. So you can see what's happening over here is when the coil turns into this angle, the forces are going to be perpendicular like this. When the coil was like that, the forces were acting like this. When the coil turns more, the forces are acting like that. And so the torque that it's going to experience is purely independent of its position. Do you get it? So the formula that I wrote there, torque is equal to BIAN, will be perfect for this situation. It will be perfect for this situation. So wherever it is, it will experience the same torque. And this way, you can have a scale, and this way the scale will be uniform. Because if 1 ampere took this ammeter pointer from here to here, then 2 amperes will take it just double. 3 amperes that way, 4, 5. It will be even scale. So the shape of the magnetic field is made into a radial magnet. So this is a radial magnetic field. You can see how the shape of the radial magnetic field is. That's called the radial magnet. And if it is absolutely flat, it's uniform magnetic. So changing the shape into a radial magnetic field has the advantage of having the same torque. Torque is equal to BIAN. And so area, number of turns, everything being constant, you can see that torque depends purely on I alone. It does not depend on the angle. And so you can have a very linear scale set up. Okay? Passing. Let me show you to this video first. Right, that's a galvanometer. And if you look inside here, and when I pass it around, you can actually have a look at it. You can actually see the coil inside. There's a rectangular coil inside. You'll see the color of a copper color. And that rectangular coil is placed in this kind of magnetic field. I don't know how well it can be focused right there. Let me see how it turns out. What is that? Oh, my pocket. All right, so when I send this around, you can actually see the coil. And when I do that, the coil will be moving. And if you look closely inside, you can also see the spiral spring. So you can see the spring as well. So if you look at it carefully, you'll see the spring as well. And this is another one which is kind of open. You can see that's the pointer is all damaged. And you can see the spring inside here also. So you can see the spring inside here. And I think the shape of the magnet is better visible in this. All right? I'll pass it around. I'm just reading out some questions. Shh. A jumper cable used to start a stalled vehicle carries a 65 ampere current. How strong is the magnetic field 6 centimeters away from it? So a jumper cable, you know the jumper cables. They're saying it's carrying 65 amperes, and you want to know how much is the magnetic field strength 6 centimeters away from it. And they're asking you to compare to the Earth's magnetic field at that spot. So 6 centimeters. So the magnetic field strength over here, the direction of course is given by the right-hand grip rule, but the focus is not on the direction. What's the strength of the field here? Magnetic field strength is mu naught I over, that's the formula for it. Substitute 4 pi times 10 power minus 7, that's mu naught, times 65 over 2 pi A, what's A? 0.06 in meters. What do you get here? Go ahead, Kristen. 2 pi, 4 pi.
2.17 times 10 to the negative 4.
2.1,
7 times 10 to the negative 4.
10 power negative 4 Tesla. And the normal strength of the magnetic field of the Earth,
So 5 times 10 to the negative
it's around that, yes. It's close to 5 times 10 power minus. Again, it depends on locations, it depends on the angle of dip and all those things. So, yeah, 5.55, something like that, 10 power minus 5. So the Earth's magnetic field is 5.55 times 10 power negative 5 Tesla. So how many times stronger is this compared to that? Is it like 4 times? Yeah, close to 4 times stronger than the Earth's magnet. So it's not terribly strong, but it all depends on how close you are. If you are pretty close, then the strength can really go up. So if you're just barely touching the wire, so you're going like almost a centimeter away. So if you're going a centimeter away, that's going to make a big difference too, like almost 25 times stronger. Right? Instead of just 4 times stronger, the strength is going to be like 25 times stronger than the Earth's magnetic field, which can mess things up. So if you have your cell phone in your pocket, and the jumper cable is going right next to the cell phone, right there, it can mess things up on the cell phone. Because magnetically, things can go wrong. I had a Toshiba before. It's still here. It's still there. The first time the whole thing crashed. The reason was my son, he had this oval-shaped magnet, and he was excited about it. He just wanted to show me that magnet, and he said, "Dad, look what I found." And he placed it right on the computer. And the hard disk was right under there. And I knew that as soon as I saw the magnet, I said, "Gone!" And the screen became blue. And I lost all the data on that one. I had to reformat the whole thing.